Welcome to this explainer. Today, we're throwing on our virtual lab coats and acting as chemical detectives. We're going to uncover exactly how substances combine in the world around us, and, more importantly, how we can cleverly pull them apart. Think about this for a second before we head into the lab. Nature is messy, right? Almost nothing out there is perfectly pure. So how do we actually manage to extract pure, life-saving medicines, or even just clean drinking water from what is essentially a chaotic, tangled soup of raw materials? Well, it all comes down to the amazing science of separation.
Here's our detective's notepad for this explainer. We'll be walking through 1. Understanding chemical mixtures. 2. Compounds versus mixtures. 3. Why we separate mixtures. 4. Basic separation techniques. And finally, 5. Advanced chemical sorting.
Let's jump right into Section 1, Understanding Chemical Mixtures, the usual suspects.
A mixture is really just a physical combination of things. It's kind of like tossing sand and water together into a bucket. The sand is absolutely still sand, and the water is still water. Every single ingredient keeps its own original identity and properties. Plus, you can mix them in any proportion you want. There are no strict recipes here, just a physical jumble of substances.
Moving on to Section 2, Compounds versus Mixtures, telling them apart.
Before we start separating things, we really have to know what we're looking at. Compounds and mixtures are fundamentally different beasts. Compounds are pure substances. They have a strict, definite composition, like how water is always exactly H2O, and you need highly complex chemical processes to break them apart. Plus, making a compound involves a change in energy. Mixtures, on the other hand, are impure. The proportions can be totally random, there's absolutely zero energy change when they form, and the best part for us detectives, we can separate them using basic physical methods.
Now, mixtures basically come in two distinct flavors. First up, you have homogeneous mixtures. This is where components, like salt dissolved in water, are completely uniformly distributed. You can't see the salt floating around, it looks like one single substance. Then we have heterogeneous mixtures. This is where the components, like our sand and water example, or say oil and vinegar, are totally unevenly distributed. You can easily spot the different parts with the naked eye.
Section 3. Why we separate mixtures. The motive.
Okay, so what's our actual motive here? Why go through all the trouble of pulling these things apart? Well, out in the real world, we usually have 3 main goals. First, to get our hands on useful substances, like taking crude oil and separating out highly useful fuels like LPG, petrol, and diesel. Second, to get rid of unwanted or harmful junk. Think about picking tiny little stones out of raw rice before cooking it. Nobody wants a chipped tooth for dinner, right? And third, to isolate incredibly pure substances, like obtaining absolutely pure water needed for car batteries or laboratory medicines.
Which brings us to Section 4, Basic Separation Techniques, the basic toolkit.
Let's crack open our physical toolkit and see how we solve these simple mysteries. Our first method is super straightforward, but incredibly effective: magnetic separation. If you have a solid mixture and just one of those components happens to be magnetic, you've got it made. Imagine a pile of iron filings mixed up with sulfur powder. All you do is wave a magnet over the top. The iron is instantly yanked out of the pile, leaving the non-magnetic sulfur completely undisturbed. Just like that, case closed. Now here's a really fascinating trick called sublimation. This happens when a solid turns directly into a vapor when you heat it, literally skipping the liquid phase entirely. Let's say you're dealing with a mix of common salt and ammonium chloride. If you put that in a dish and heat it up, the ammonium chloride sublimes. It turns straight into a vapor, floats upward, and then solidifies directly onto a cool surface above it like an inverted glass funnel. The common salt, which definitely doesn't sublime, is just left sitting there perfectly behind. But what about solid liquid mixtures? Well, if a solid is insoluble, meaning it stubbornly refuses to dissolve like sand or chalk in water, we just use basic filtration. We pour the mixture through filter paper, the liquid passes right through as filtrates, and the solid is trapped behind as a residue. But what if the solid did dissolve, like salt in ocean water? For that, we use evaporation. We just crank up the heat until the liquid boils away completely into vapor, leaving our solid salt safely behind in the dish. Time to level up. Section 5, Advanced Chemical Sorting, the masterclass. Because sometimes, physical separation isn't as easy as waving a magnet. This brings us to a really fun puzzle. How on earth do you separate 2 homogeneous liquids that have blended totally seamlessly into each other? We call these miscible liquids. Think alcohol and water. You can't filter them, and you certainly can't just pluck them out with tweezers.
We crack this specific case with a brilliant technique called fractional distillation. It relies entirely on one simple fact. Different liquids boil at different temperatures. Water boils at 100 degrees Celsius, right? But alcohol boils at just 78 degrees. So by carefully controlling the heat in a distillation flask, the liquid with the lower boiling point, our alcohol, vaporizes first. Those vapors travel up a fractionating column, cool down, condense right back into a liquid, and simply drip into a completely separate container.
And we actually do this on a massive industrial scale every single day with crude petroleum. Crude oil is this incredibly complex mixture, but by heating it up in a giant fractionating column, we can extract everything from heavy lubricating oil way down at the bottom, all the way up to diesel, petrol, and petroleum gases at the very top. We do it all simply by capturing their specific vapors at different temperature points. It really is chemical sorting at its absolute most powerful. Okay, another really advanced tool we use is chromatography, which literally translates to color writing. It's this incredibly clever three-step method. You take a stationary phase, like a strip of special filter paper, and you dab a tiny drop of your mixture on it. Then, you dip just the edge of the paper into a moving liquid solvent, called the mobile phase. As that solvent slowly creeps up the paper, it drags the mixture right along with it. It ends up separating the components based on how well they stick, or adsorb, to the paper versus how soluble they are in the liquid.
If you were to watch this process happen, it's pretty amazing. Different dyes hidden inside a single, tiny drop of black ink will travel up the filter paper at totally different speeds. The highly soluble dyes race ahead to the top, while the less soluble ones lag behind. It literally unpacks all the hidden colors right before your eyes. It's an elegant tool used for everything from analyzing dyes to testing blood and drugs in forensic labs. And finally, Section 6, the ultimate test, a multi-component mystery.
All right, detectives, final exam time. Let's put everything we've talked about together. Imagine you're handed a totally chaotic, dry mix of iron filings, sand, and salt. How do you isolate all three? Well, we just sequence our tools chronologically. Step 1, run a magnet over the dry pile. Boom, the iron is immediately extracted. Step 2, you're left with sand and salt. So, add water. The salt easily dissolves into a solution, but the sand just sits there. Pour that whole mess through filter paper, the sand gets trapped, and the clear salt water passes through. Step 3, take that salt water, apply some heat, and evaporate the liquid entirely to reveal the pure salt. See? We just conquered a complex mixture by systematically applying simple, everyday physical principles.
As we wrap up this explainer, I want to leave you with a thought. The stuff we just talked about, magnetic separation, distillation, filtration, it's not just some textbook exercise. It's exactly how we manipulate the physical world around us. So how will you apply these very same chemical detective skills to untangle the massive environmental mixtures of our future? Whether that's figuring out how to recycle the incredibly complex components inside electronic waste, or filtering microplastics out of our heavily polluted oceans. The toolkit is there, it's yours to use. Keep investigating.